Today we're going to look at the Bioenergetics 1 PowerPoint, or that's the name of the PowerPoint in your Brightspace folder. So we're going to talk a little bit about thermodynamics and we'll go from there. Let me remind you, I'm leaving this in non-presentation mode so I'm able to write on the slides. In presentation mode, I'm not able to do that. So we're going to look at thermodynamics a little bit and a little differently than you've probably done in the past. In physical chemistry, if any of you have taken that, you get into it pretty deeply. We're not going to do that, and we're not even going to do the calculations that you did in general chemistry. The reason is that in general chemistry, you tend to do the calculations, hope you get the right answer, get your points, move on to the next question, but not really think about what that number, what that means. We're going to focus more on what that result means and what information are we getting from it. So a few little reminders. Our system is the molecules, cell, tissue, whatever we define it to be. Everything else is our surroundings. Don't forget, enthalpy is the heat content of the system. So enthalpy is the heat contained in the system, while temperature is something telling us how hot or cold the system is. So don't confuse those two. Of course, entropy is the randomness or the disorder of the system. So in general chemistry, you spent a decent amount of time talking about the first law of thermodynamics, second law, and so on. There's so many different ways of expressing both of those. The first law says that the total energy of a system and its surroundings is constant. A really common way of hearing it expressed is that energy can neither be created nor destroyed. I kind of like that one because energy is moved. So what do I mean by that and how does that apply to us? Well, what I mean is this. Let's say you ate something. You just ate your peanut butter Oreos. So you ingested your food, your fuel, your calories. Don't forget what calories really are. Calories are a unit of fuel measurement. So I took in whatever amount of energy that I quantify as whatever number of calories. So what do I do with that? Well, what I do is I go through all the steps, the reactions, the processes that we'll do in the second half of this course. And when I call the course halves, I I mean half of the whole thing, combining first and second quarter. So we actually start the second half of the course around week 8-ish. So all the stuff we're going to do in the second half will take those calories and turn them into a usable form of energy for your cells. Your cells can't use peanut butter Oreos, so they need the energy in a different form. So we'll talk about how we get there. But all we do is move the energy from the Oreos to the form the cells need. So we have different types of energy. We have kinetic energy. You talked about that in general chemistry, heat, random motion of molecules, things like that. We have potential energy. That would be me standing on the top of one of the buildings ready to drop a ball or something. So that was something you talked about in Gen Chem. The second law of thermodynamics says that the total entropy of a system and its surroundings always increases for a spontaneous process. So we'll talk about that too. So first law, energy of the universe is constant. We only have two ways of transferring energy, heat and work. So the change in energy of a system is equal to the sum of the heat that flows into the system plus the work done on the system. So we'll apply that. Second law, we're always going to equilibrium. We have a preferred route to equilibrium. Equilibrium is one of those things that kind of makes you forget something for a minute. So here's what I mean by that. We're always moving to equilibrium. Here's the catch. Not all equilibriums are good equilibriums. So sometimes when you see the cells, the tissues, whatever, heading towards a bad equilibrium, you're thinking, oh, that can't be right. That can't be what's happening. It can be. But here's the thing. You can go to that bad equilibrium, then you can say, well, I'm going to regroup and go to a new, better equilibrium. So equilibrium is not permanent. We can go to one equilibrium, then go to another equilibrium. Sorry, I got stuck for a minute. Okay, so let's talk about entropy. Here's the thing with entropy. I can have, and this is just an example, I can have some oxygen in a container, hydrogen in a container, and let's say it's one container with a divider. I'm nice and organized there. I have one molecule, type of molecule on one side, my oxygen, I have hydrogen on the other. Then let's say I remove that divider. All my oxygens mixed with all my hydrogens. Well, what did I do? I increased the entropy. I went from a nice orderly system to a not so orderly system. But, that's one equilibrium. Then what can happen? Well, I can take my random oxygens and hydrogens I have all floating around together and allow those to react. So my hydrogens can react with my oxygens and make me hydrogen peroxide. Nice and organized now, a new equilibrium. But what happens when I do that? The entropy in my system, my little container, decreased because I put heat out into the rest of the world. So I increased the entropy of my surroundings. Typically, we used to talk about proteins before we did this PowerPoint or this topic. So what we do when we talk about proteins is we talk about how we form a protein from amino acids. So we attach the amino acids to each other. We talk about what kind of bond does that. And then we talk about what other bonds take place between parts of the polypeptide molecule that we're forming. So as we go through this discussion, we're organizing this molecule a little more, a little more, a little more as we go. So we start out with a higher entropy in our disordered mixture, and then we fold and we organize and we bond and we organize. So we make these nice, organized, folded polypeptides. We're lowering the entropy as we do that. So you'll see this entropy theme through a lot of the things that we do. Okay, so where are we going with this? Where we're going with this is Gibbs free energy. Gibbs free energy of the reaction. Gibbs free energy is a function of, or the change in Gibbs free energy of reaction is a function of the change in the enthalpy of the system, the temperature, and the change in entropy of the system. The reason I bring this up is that we're not going to do the calculation. So when you don't do the calculation, it's easy to kind of feel like that number came out of thin air. So we're doing this to remind you the number didn't come out of thin air. So delta G is a function of all these things. So really important to remember, really easy to ask you a question on that. And the question would be something like delta G is a function of all of the following except. So of course it is a function of these three things. Your except is going to be something else. I'm bringing this up and telling you this to make you really focus on this. I want you to realize that even though we're not doing the calculation, the number is not coming out of thin air. Okay, so why do we care about delta G? What is it telling us? So delta G of reaction is actually the free energy contained in the products minus the free energy contained in the reactants. So you did that calculation in general chemistry. So this is where you went to that table in the back of the book that felt like it was written in about a 2-point font. After you did a couple of these, you thought you were going blind or cross-eyed or both. But what you were doing was looking up the energy of the products, looking up the energy of the reactants, and doing products minus reactants. You cared not only about what number you got, you cared about what sign you got. Is it positive or negative? So here's why you care about that, or why you did care about that. The sign tells us whether the reaction is going to go or not. So this is one of the big things with delta G. Delta G is independent of the path of reaction. So delta G is products minus reactants. Is the reaction going to go or not going to go? It's nothing about how it's going to go. So it's like if I asked you, are you going to Orlando this afternoon? You can only tell me yes or no. You can't tell me how you're getting there, what route, what means of transportation. Are you taking a bus or a bicycle or your car or whatever? Just, are you going or not? Period. No details. So all that other stuff I talked about, car, bus, bicycle, route, that's the path of reaction. Delta G tells you nothing about the path of reaction because it's independent of the path of reaction. Where that gets confusing is the place where you start talking about or thinking about enzymes. So let's back up and talk about enzymes for a minute. Here's the thing with enzymes. Enzymes are all about that path of reaction. Remember how enzymes work. Well, first, what they do, they increase the rate of reaction. Well, rate's all about path. How do they do it? They do it by decreasing the activation energy or decreasing the energy of the transition state. That's how they increase the rate of reaction. But again, that's all about what's going on in the middle between reactants and products, all about the path of reaction. So enzymes make the path of reaction easier and as a result faster. Delta G is independent of the path of reaction. This is the reason actually that I rearranged the order in which we talk about these topics. What I noticed is if you get questions on enzymes independently or delta G independently, the statistics are much higher on those questions than if I put exactly the same questions back to back, an enzyme question with a delta G question. So since I saw the stats drop significantly when I did that, I want to make sure you're really, really solid on it. So enzymes are all about the path of reaction. They make the path of reaction easier and as a result make it faster. So all about the path of reaction. Delta G is just a go or no go, totally independent of the path of reaction. It's just telling you whether the reaction is going to happen or not. So the first delta G we're going to talk about is a reaction for which delta G is negative. So delta G is negative. That's called a spontaneous reaction. Well, that kind of gets you in trouble a little bit right there with this time frame thing. So here's the thing with the word spontaneous. The word spontaneous has a different meaning whether we're applying it to chemistry versus the way we tend to use it in our everyday language. So in everyday language, spontaneous has the implication of fast. So if somebody makes a spontaneous decision, the implication is they made a fast decision without researching it or whatever. So the implication is that of a fast decision. However, in chemistry, all spontaneous means is that I have enough energy contained in those reactants for those reactants to become the products. So spontaneous just means that the reaction is going to go. Doesn't tell you whether it's going to go fast, going to go slow, just that it's going to go. So be very careful with that word spontaneous. It's a good word for someone to use if they want to try to mess you up on a question and make you say that delta G gives you any information about the rate. It doesn't. just totally independent of rate because it's independent of path. So that's our spontaneous. But intuitively, negative as a go doesn't quite sit intuitively. So go back to what delta G is. It's products minus reactants. So if delta G of the reaction turns out to be a negative number, the only way it can be a negative number is if the reactants contain more energy than the products. So if the reactants contain more energy than the product, it's like a downhill trip from reactant to product. So because of the way we calculated products minus reactants, negative means it's going to go because I have more energy contained in the reactants than I do in the products. The next one we're going to do is that of a positive delta G. So if delta G is positive, that means the products have more energy than the reactants. So I need to fill that energy gap to get there. So the products have more energy than the reactants. I need to fill that gap. So the only way I can get from those reactants to products is I have to put energy in. I've got to add work, add energy. So a positive delta G means I positively have to put energy into the system for that reaction to go. You'll notice on everything we have this constant temperature and pressure little disclaimers on here. Oops. And I'm pointing it out because it's something we kind of ignore. We're making that assumption. We're at constant temperature, we're at body temperature. We're at constant pressure, we're at atmospheric pressure. Because we maintain that assumption, we really don't talk about it. So I want to point this out. I don't want you to get thrown off when you see that on a question and say, well, what delta G were we talking about? Were we constant or not constant? We're always constant temperature and constant pressure. We're now also constant pH because we've buffered. Okay, the last situation is delta G equals 0. That's a reversible reaction. So for delta G to equal 0, that's a reversible reaction. Super easy, so easy that it's easy to kind of lose the forest for the trees on this one. What we tend to do is focus so much on our positives and negatives, which one's going to go, not go, whatever. Then we'll get to a reversible reaction and we'll say, oh, hang on, what happens here? It's not positive, meaning I need to put energy in. It's not negative, meaning it's just going to go. What's happening? Well, remember what regulates a reversible reaction. It's equilibrium, right? So this is the whole Le Chatelier story. So what did Le Chatelier say? If I had a system that's in equilibrium and I do something to mess up that equilibrium, which of course we mess up equilibriums by adding or taking away product or reactant. So if I do that, the system will adjust to restore the equilibrium. So pretty easy. Just whichever way it goes to get out of equilibrium, it's going to shift to go back. Okay, so how do we apply all this? Let's say we have our little fakey process. So I have all these steps, all these reactions that take A to F. So I have some delta G's of these. So delta G of A going to B is minus 10. We'll make B to C reversible. Okay, so I just made up some numbers here. So I just made up some numbers, but it's typical of a process that we're going to do. We'll have some positive delta G's, we'll have some negative delta G's, and we'll have some delta G's equals 0. So how do I know if this process is going to go or not? Well, what I'm going to do is I'm going to figure out my overall delta G. So that's going to be the sum of all my delta G's. So minus 10 plus 0 plus 20 minus 15. So my overall delta G then, my sum of all this is going to be what? Going to be minus 5, right? So it's going to be minus 5. So because I have an overall negative delta G, I'm going to be a go. So every process we're going to do is going to have an overall negative delta G. Well, how do I get the positive delta G reactions to go? You'll hear the expression that another reaction carries it along, drags it along, things like that. And that's exactly what happens. So this is kind of like, the first week in your office, you make money. So you made $10, whatever. The next week in your office, you made and spent the same amount. So you were just flat that week. Then the third week of the month, you bought all your supplies for your office. You paid all your bills. Your staff's payday is that week, whatever. So that week, your overall is minus $20. And I know these aren't office numbers, but just go with it. Then the last week of the month, you had money come in, nothing go out. So what did I do? I had 25 come in and 20 come out. So my overall money for the office is plus $5. And again, I know they're not office numbers. So I'm in the positive here, money-wise, and a minus delta G is a go. So just like one week supported a couple other weeks type of thing, one reaction can support another reaction. Okay, so again, remember that spontaneity just means the reaction is going to go. Nothing to do with rate of reaction. So delta G is independent of the path of reaction, as in it tells you nothing about the rate of reaction. So that's why you need to be very, very careful of that word spontaneous. So delta G can be negative, that's our go. Positive, no go. Equal to 0, that's just equilibrium controlling it. If I get out of equilibrium, I'm going whichever direction I need to get back into equilibrium. So the key to all of this is a molecule called ATP. So we're going to talk about that in a minute. We've got a couple of definitions to do first. And like always, I'm keeping your definitions to a minimum. It's not a definition class, but there is stuff you need to know. So I have two definitions that go together. Don't blend them. I can have a catabolic reaction in which I break big molecules down into small molecules. So I can have, a 6-carbon molecule, I break into 2 3-carbon molecules. That's catabolic. It's a big catastrophe. I broke something. I can have an anabolic reaction. We think of it as building up cells. But an anabolic reaction can take little molecules and make big molecules. All metabolic processes involve energy. That we're going to have reactions where energy goes in, we're going to have reactions where energy comes out, and then we'll have reactions that delta G equals 0. If energy is going in, it's an endergonic reaction. If energy is exiting, it's an exergonic reaction. So don't let these concepts cross. I'll hear you guys saying, well, a catabolic reaction has to be exergonic, or anabolic has to be whatever. I can give you examples of catabolic endergonic, catabolic exergonic, catabolic that are delta G equals 0. Same thing with anabolic. So if you try matching anything here and here, you're just going to get messed up with it because there's more exceptions than the rule on some of those. Okay, so the key to all of this is a molecule called ATP. We've talked about ATP a little bit, but we're going to talk about it more. So ATP is adenosine triphosphate. Make sure on any molecule that we abbreviate that you're okay seeing it spelled out. Reason being is that right now the boards like everything spelled out. So if you're very focused on ATP and don't know what ATP means, stands for, and then you get a question that you know the answer is ATP, you're looking and saying, well, which is it? You're not giving me the right answer here. They probably just spelled out adenosine triphosphate. So be very comfortable with that. I'll abbreviate it through the whole course, but anything we abbreviate, make sure you're okay that you'll recognize it when it's spelled out. So here's what adenosine triphosphate is. I have a ribose and I have an adenine. When you put ribose and adenine together, you get adenosine. That's great, but that's not really the business end of the molecule. Then I have three phosphates attached. The three phosphates are attached through high energy phosphate bonds. That's the business end of the molecule. So here's what we do. We use the fact that we have these three phosphates attached in high energy phosphate bonds. So ATP is like biochemistry money. So we're going to be kind of budgeting ATP. So it's like when you do your regular budget, whether it's your personal, your office, whatever. You're looking at how much money comes in versus how much money comes out. And you've always got to follow both. It's almost like the numbers don't matter, the difference between the two matters more, if that makes sense. So I didn't word that very well, but you know what I mean. If you have a ton of money coming in, but more going out, it's still not working, I guess is what I'm trying to say. So here's what we do. We have ATP. Those phosphates, the P's, are attached in high energy phosphate bonds. So if I break a high energy phosphate bond off, I'll take the phosphate and do whatever with it. But when I break that high energy phosphate bond, I get energy. So I get the energy, and then I'll have ADP, adenosine diphosphate. So I took the phosphate off. I might put it on something, I might not, depending on the reaction and what I'm doing. But I absolutely got the energy to go and drive a reaction or whatever I need to do with it. Then I can take the ADP, because this one's gone now. I can break another high energy phosphate bond and get more energy. I can send the phosphate somewhere, maybe attach it to something, maybe not, but that was energy coming off again. So I broke a high energy phosphate bond because I wanted energy. Then what I can do, let's say, then that would have me down to AMP, adenosine monophosphate. I had gone from ATP. So now let's say I'm at AMP and I just ate some peanut butter Oreos. So I ate some peanut butter Oreos. I'm going to ADP now. So I want to put that phosphate back on. Well, that's all well and good, but the only way I can put that phosphate back on is this. I need energy to replace, to make that high energy phosphate bond. That's where my Oreos come in. The calories from those Oreos, the fuel, the food that I ate, I go through all my steps, all my stuff, all my processes, and I convert it into the energy or the form that makes this bond. Now I have ADP. Then let's say I eat another Oreo. So I eat another Oreo. I have those calories. Well, what I want to do is I want to put this phosphate back on. So I want to put that phosphate back on now. What else do I need besides the phosphate to go on? I'm going to take the calories from the food that I ate and turn it into energy to make another high energy phosphate bond. So we're always going to be counting and accounting for how many ATP. I want you to get very tuned into looking at ATP in this way. Look at ATP like a price tag. Like if you go shopping, you're looking at price tags on whatever you're shopping for, and you're doing your comparing and making your decision. But looking at that number is a big factor in that. So look at ATP like a price tag. If I'm using ATP in a reaction, a process, a series of reactions, or whatever, and they're going to ADP, then I'm using energy. That reaction is costing me energy. So it's like a price tag costing me money. Or let's say I have a process that's making me ATP. I'm putting ADP in and I'm getting ATP out. It's kind of like price tags, but I'm getting paid this time. So I'm getting paid for doing that. You're giving me energy for doing those steps, doing those reactions, doing that process. ATP is coming out. So get very clued in, keyed into that because it's really important for figuring out what's going on as we go through our steps, our stuff, our processes. Okay, so I just drew the line and kind of slashed one off, but here's my adenosine triphosphates. I have three phosphates on there. Then if I break this high energy phosphate bond, I'm down to two. Adenosine diphosphate. Break that bond, I'm down to one adenosine monophosphate. So here's the thing when we do this. I've got a lot more energy contained. Let's go back to the previous slide and do this. I have a lot more energy contained in the bond connecting the third phosphate than I do in the bond connecting the second phosphate. So let's talk about that. And I'm going to use a money analogy again. And I know you guys hate my money analogies, but that's okay. If you don't figure out the money in your office, you're going to have a problem. I know you're in this to help people, but if you can't keep a roof over your head, you're not going to help as many people. So it is important, and please don't email me about it. So this is a higher energy phosphate bond. We have to think in money. That's why I do the money. So let's say I get $10 for breaking that bond. This one now is lower energy. Let's say I only get $5 out of breaking that one. So I have my $10 bond and I have my $5 bond. So what would you rather do? Would you rather take one ATP to AMP or two ATPs to two ADP? Well, I don't know. Let's figure it out. So going from ATP to AMP, what am I doing? Well, I'm going from ATP to ADP. That's giving me $10. I'm going from ADP to AMP. That's giving me $5. So I get a total of $15 for doing that. Or if ATP to ADP is $10 times 2, now I'm at $20. So that one's actually the better deal. That one's the better deal. I get $20 going from ATP to ADP times 2 versus 15 going to AMP. So for that reason, we're going to do primarily, there's one exception in what we'll do. We're going to primarily go ATP to ADP, then replace the phosphate and the energy back to ATP, use it back to ADP, back and forth, back and forth. So we're going to do that rather than going all the way down to AMP with one exception. So I made up the numbers just to have round numbers for my 5 and 10. The ratio is roughly proportional, almost twice as much ATP to ADP is ADP to AMP. So if my numbers and the dollar part bothers you, you can actually redo that slide with the real numbers here. Okay, so let's throw a little disclaimer in. We've always got to have a disclaimer. So the numbers we have are ideal theoretical numbers. So in that little diagram that I did with my A going to B, going to C, going to D, let's go back to it. If I did this diagram where I ended up with a 0 here, it's not reversible, but it's also not going to go. I need a little bit of wiggle room here because these are ideal theoretical numbers. But here's the thing. You don't have ideal theoretical cells. You have plain old real world cells. So it's kind of like the new car that you bought that has the window sticker that says you get 30 miles to the gallon. You know darn well if you put 1 gallon of gas in because you were going 30.000 miles, you're going to end up pushing it. You're not getting there. That's under ideal, theoretical, downhill with a tailwind on slippery ice kind of numbers. So, same thing. I need a margin, I need room, I need a margin of error here because it's ideal, theoretical.